You know what keeps me up at night? That big fundamental question. Are we the only show in town, cosmically speaking?
It's a huge question.
Well, you're not going to believe this, but we've just gotten what could be some seriously exciting first clues from a world unimaginably far away.
Exactly. Today, our deep dive takes us 124 light years out to the constellation Leo.
Wow.
We're looking at the exoplanet K2-18b, and we're going to unpack the very latest findings from the James Webb Space Telescope.
JWST. Yeah.
Observations that have scientists, and likely you listening, really pondering the potential for life beyond Earth.
Think about that. 124 light years. That light's been traveling for over a century to get here.
Mm-hmm.
And now, maybe, just maybe, it holds an answer to that question. You know, if this pans out, it's huge.
It absolutely could be. It changes everything about how we see ourselves in the universe.
It could finally answer that, that alien life question everyone wonders about.
Right. And what's great is that you shared some really compelling reports, including that CNN coverage, detailing these initial Webb observations.
Yeah, trying to get my head around it.
So we're going to dissect what these amazing instruments picked up and what the first potential implications might be for everyone listening and for science.
Okay, so mission for today's deep dive. Let's get straight to the important stuff. These potential hints of life on K2-18b.
The core nuggets.
Exactly. Why are people so excited? But also, let's cover the cautious side, right? The understandable hesitation.
Definitely need that balance.
We want to give you the key info without getting, totally bogged down in jargon. So let's set the scene. K2-18b. What is this place?
Okay, so picture this. K2-18b. It orbits a red dwarf star.
Smaller than our sun, right?
It's cooler, too. And it's way out there, 124 light years away. But the key thing is its location. It's in the habitable zone.
Ah, the Goldilocks zone.
Precisely. That sweet spot where temperatures could allow liquid water on the surface.
And water is, well, essential.
It's the fundamental thing we look for, based on life as we know it, a primary criterion in the search.
Okay, so location's good. But I kept seeing this term, Hycean world. What's that about?
That's a great question. It's a relatively new concept, really. A Hycean world is thought to have a hydrogen-rich atmosphere over a huge ocean, maybe even a global one, like a water world, but with a very different sky.
And we think K2-18b might be one.
Previous data hinted at it. They found methane and carbon dioxide, which you might expect. But crucially, there was a lack of ammonia.
And that fits the Hycean model.
It does. Ammonia would be expected under different conditions, so its absence supports the idea of a water ocean interacting with that hydrogen atmosphere.
So definitely not Earth 2.0 then. It sounds quite different.
Oh, not at all. K2-18b is a beast compared to Earth, about 8.6 times the mass.
Whoa.
And roughly 2.6 times the radius, so significantly larger.
And why is that important for us thinking about life?
Well, it broadens our horizons, doesn't it? We're not just looking for rocky planets exactly like ours. Maybe life can find a way on these bigger, watery worlds, too. It opens up the possibilities.
All right, different kinds of planets might be in the game. Okay, so big potential water world, hydrogen sky. Now, the Webb telescope. What did it actually see? What's the big news from your sources?
This is the core finding. Webb's latest observations detected chemical fingerprints, strong suggestions of dimethyl sulfide DMS.
DMS?
And possibly dimethyl disulfide as well, DMDS, in the planet's atmosphere.
DMS, DMDS. Okay, chemistry wasn't my best subject. Why are those molecules a big deal? Why should we care?
Okay, this is where it gets really exciting. On Earth, DMS is basically only produced by life.
Only?
Predominantly, yes. Marine phytoplankton, mostly. Those tiny ocean microbes.
Wow.
So finding DMS is considered a potential biosignature, a chemical clue, like a cosmic breadcrumb pointing towards life.
Okay, potential biosignature. So are scientists shouting from the rooftops, "We found aliens"? Is it that clear-cut?
No, definitely not shouting it. And this is where the crucial caution comes in. You really need to understand the nuances here. The scientists involved and others looking at this are being very, very careful. It's tantalizing, incredibly so, but it's not definitive proof.
So there could be another explanation.
It's possible. Maybe some unknown non-biological process, some weird chemistry happening under K2-18b's specific conditions could be making these molecules. Less likely, perhaps, but possible.
Okay, that makes sense. Can't jump the gun. But how strong was this signal? Was it faint, easy to miss, or?
They report the DMS detection at the 3 sigma level.
3 sigma, what does that mean, practically?
So think of it like this. It means there's only about a 0.3% chance the signal happened randomly. It's a pretty strong hint.
Okay, 0.3% chance it's random noise. That sounds pretty good.
It is good. But in physics and astronomy, the gold standard for a discovery is usually 5 sigma, which is much, much stricter, like a 1 in 3.5 million chance of being random. So 3 sigma is significant evidence. It makes you look closer, but it's not considered definitive proof yet. Keeps the possibility of a false positive on the table, however small.
Got it. So a really strong lead, something to follow up on, but not case closed. Now, I think I read this wasn't Webb's first look at K2-18b.
That's right. These new results used Webb's mid-infrared instrument, MIR.
MARI, okay.
But they build on earlier observations with other Webb instruments, NIRS and NIR-SPEC.
And what did they see before?
Those earlier observations already found the methane and carbon dioxide we mentioned. And interestingly, there was maybe even a faint hint of DMS back then, too.
Oh, really?
Yeah, but this new detection with MIRI is much clearer. And crucially, it's independent. Different instrument, different wavelengths of light.
Okay, so it's like getting corroborating evidence. 2 different witnesses seeing something similar. That makes it sound more robust.
Exactly. It strengthens the case significantly. It's not just one instrument possibly acting up.
And the reports you shared mentioned the signal came through strong and clear this time.
Absolutely. The researchers seemed quite encouraged by how unambiguous the signals appeared in the MIRI data this time around. Not faint or borderline.
Okay, so the team doing the work is excited but cautious. Standard scientific process, really. What about other experts? What are the big caveats, the things we need to keep firmly in mind here?
Well, the number one thing everyone agrees on is more data. Lots more data.
Right. Confirmation needed.
The study team itself thinks another 16 to 24 hours of Webb observation time focused just on this could be crucial.
That's a lot of telescope time. It's precious.
It is. But that shows how important they think this is. They need to really solidify the results, maybe see if the signal persists or changes.
And what about that other possibility that DMS isn't from life, the abiotic source idea?
That's a huge focus. Can we dream up a non-living chemical pathway that makes DMS under K2-18b's conditions? You know, high pressure, hydrogen atmosphere, potential water interaction.
The unknown chemistry, basically.
Exactly. We have to rigorously rule that out before claiming a biosignature. That's a critical step.
I also saw in the material you sent over that some big names in the field, like Sarah Seeger, were suggesting K2-18b might be totally different anyway.
Yes, that's another layer of complexity. Dr. Seeger, who's a giant in exoplanet research but wasn't part of the study, pointed out alternatives.
Like what?
Well, one possibility is maybe it's not a Hycean world at all. Maybe it has a boiling hot magma ocean.
Magma. Okay, that's definitely not habitable.
Not as we imagine life, no. Or, she suggested, it could be a mini Neptune.
A mini Neptune, like a gassy planet.
Sort of. Bigger than Earth, smaller than Neptune, with a really thick, deep atmosphere. That might mean there's no surface liquid water, even if the temperature is right. The pressure could be too immense.
So the very nature of the planet itself is still debated, whether it's even potentially habitable in the first place.
Among some experts, yes. The Hycean interpretation seems strong based on current data, but these alternatives need to be considered. It adds context.
Okay. And because of all this uncertainty, the planet type, the DMS source, Seeger thinks this will stay a candidate for a while.
That's her feeling, yes. That it'll likely stay in the candidate category indefinitely because proving it one way or the other requires so much more investigation. It's not a quick answer.
Right. Sounds like this is going to take years, maybe decades, of follow-up work.
Very possibly. Science at the cutting edge often moves slowly and carefully.
It made me think, though, scientists have been looking for these out-of-place gases for a long time, haven't they? Gases that hint at life.
Oh, yes. Back nearly a century, James Jeans was talking about oxygen in Earth's atmosphere. Why is there so much O2?
Because plants make it.
Exactly. It's so reactive, it shouldn't just hang around unless something, i.e. life, is constantly pumping it out. That's the same basic idea here with DMS, just on another world.
Find a gas that shouldn't be there without biology.
That's the principle. But with exoplanets being so far away and hard to study, the risk of misinterpretation is high. Jumping to conclusions is tempting but dangerous scientifically.
So this DMS detection, even if real, needs to clear that very high bar.
Absolutely. And there's research by Eddie Schwieterman's group at UC Riverside that looked into this specifically.
What did they find?
They calculated how much DMS would need to be produced on K2-18b to match the levels the Webb data might be suggesting.
Yep.
The production rate would need to be enormous, something like 20 times the total DMS produced by all life on Earth.
20 times Earth's total. Wow.
Yeah. That's a, quote, high bar for any non-biological process to achieve. It makes the life explanation seem, well, more plausible, or at least very intriguing, because life is known to be incredibly productive.
That's a fascinating calculation. It does make the non-life explanation seem tougher. But I also saw other scientists stressing the need for independent checks.
Yes, essential. Peer review and application. Dr. Madhusudan, the lead author on the Webb paper, said their data is being released publicly very soon, like next week.
Okay, so other teams can grab it.
Exactly. Other groups around the world can download the raw data, run their own analysis, use their own software and techniques.
And see if they find the same DMS signal.
Precisely. Do they see it? Is it as strong? Do they interpret it the same way? That independent validation is absolutely fundamental to how science confirms discoveries.
That makes perfect sense. Open data, multiple eyes, checking the work. Now, back to Schriederman for a second. He also mentioned something about ethane being missing. That sounded important.
Yes, that's another really interesting piece of the puzzle, a potential sticking point.
How so?
Based on our current understanding of atmospheric chemistry, if you have a lot of DMS or DMDS floating around,
Okay.
the ultraviolet light from the star should break it down.
Right, UV radiation.
And one of the expected byproducts of that breakdown is ethane, C2H6.
Okay, so we should see ethane if there's lots of DMS.
Our models predict we should. But Webb hasn't detected ethane on K2-18b so far.
So what does that mean?
Well, a couple of possibilities. Maybe our atmospheric models for these weird Hycean worlds aren't quite right yet. Maybe the chemistry is different than we expect. Or maybe there isn't actually as much DMS or DMDS as the initial signal suggests. Maybe the signal itself needs a closer look. The absence of ethane definitely raises questions.
It's like a detective story with conflicting clues. Need more evidence.
That's a great analogy. Lots of pieces still need to fit together before we see the full picture.
Okay, so lots of caveats, lots of wait and see. But even with all that, just talking about a potential biosignature on a Hycean world, that feels like a big step, doesn't it? What are the broader implications here?
Oh, absolutely. This is potentially huge for future searches. Hycean worlds seem to be pretty common out there, maybe more common than rocky, Earth-like planets in the habitable zone.
Really? More common?
Current estimates suggest they could be, yes. So if these worlds can host life, even microbial life-producing DMS...
Then we've just massively expanded the number of places we should be looking.
Exactly. It broadens the search strategy enormously. We're not just hunting for Earth's twin anymore. The universe of potential homes for life just got much, much bigger.
That's incredibly exciting. It really shifts the perspective. And it highlights how amazing our tools are getting.
Totally. The James Webb Space Telescope, its power to dissect the light filtering through an exoplanet's atmosphere hundreds of light years away.
And pick out these faint chemical signals.
It's revolutionary. It marks a new era in the search for biosignatures. We just couldn't do this kind of detailed atmospheric chemistry before. It opens up so many possibilities.
Possibilities that also raise some really deep questions for us, philosophically.
For sure. Niku Madhusudan, the lead author, brought this up too. If we do find life, even microbes, are we ready?
Ready for what that means.
Yeah. How does that change our understanding of ourselves, our place, and what even is life on a world so different from Earth? Does it fit our definitions?
Big questions, things that go way beyond the science itself.
They really do. These are questions that suddenly feel much more immediate, more relevant, thanks to findings like this.
Okay, it's a lot to take in. Let's try to boil it down. What are the absolute key takeaways from this deep dive on K2-18b?
All right, the main points. James Webb Space Telescope saw potential signs of dimethyl sulfide, DMS, on K2-18b.
And on Earth, DMS means life.
Primarily, yes. Making it a potential biosignature. But big, but huge caution is needed.
Right, not confirmed.
Not confirmed. Need much more data, follow-up observations, independent checks to rule out non-biological sources.
Okay.
Still, it's exciting because it puts these Hycean worlds, these potential water worlds with hydrogen atmospheres, firmly on the map as promising places to look for life. And they might be common.
Got it. Promising hint, not proof. Need more work. Highlights new places to search.
That sums it up pretty well.
This news, it just sparks the imagination, doesn't it?
Yeah.
Even with all the caveats, it's amazing to think we're even having this conversation.
It really is a testament to how far we've come in exploring the cosmos. And these telescopes are only getting better. The discoveries are likely just beginning.
So here's a final thought to leave everyone mulling over today. K2-18b, if it is a Hycean world, is so incredibly different from Earth.
Radically different.
So what other kinds of life maybe forms we can barely imagine, living in ways we haven't conceived of. What other kinds of biosignatures might we be completely missing right now, just because we're so focused on finding things familiar to Earth?
That's the billion-dollar question, isn't it? What else is out there waiting to be found if only we knew how to look?
That's something to think about. Thanks for taking this deep dive with us.